Hello everyone, as always, welcome back to my YouTube channel Algoptimize. Today we are going to learn about an algorithm called Bellman-Ford Algorithm. This algorithm is used to solve the shortest path problem. In shortest path problem, we have to find the shortest path between two vertices or nodes in a graph. To find the shortest path, we can use algorithms like Dijkstra algorithm, Bellman-Ford algorithms and Floyd-Warshall algorithm. Dijkstra algorithm and Bellman-Ford algorithm is used when there is a single source node, and the difference is that Dijkstra algorithm cannot be used when there are negative weights, and Bellman-Ford algorithm can be used when there are negative weights. And in Floyd-Warshall algorithm, we use it to find shortest path for all pairs in the graph. Now, let's see how to use the Bellman-Ford algorithm. In a graph, there are two main components like vertices or nodes and edges. Vertex means heap and an edge means a connection or a relationship between two vertices. In this video we are using directed weighted graphs, which means that every edge has a direction, a weight assigned to it. Weight is a numerical value assigned to an edge to represent capacity, time, cost, distance or strength of the edge. For Bellman-Ford algorithm, we use iterations to find the shortest path. And to calculate the number of iterations, we can use V minus 1 formula, and V represents the number of vertices. In each iteration, we can update the current shortest path if distance V is greater than distance U plus weight of U to V, in which distance V represents the current shortest path and distance U plus weight of U to V represent the cost of another path. And if this condition is satisfied, we can assign distance U plus weight of U to V as distance V. This process of path updating is called as edge relaxation process, which means to smaller the weight if possible. Let's see how edge relaxation is done step by step. As an example, there is a graph containing three vertices like A, B and C, and the source node or vertex is A. From node A to B, the weight is 2. From node A to C, the weight is 5. And node C to B, the weight is 1. The first step of edge relaxation is initializing. In here, A is 0 because from A to A, there will be no cost. For B and C, the path is still not defined. So, we represent it with the infinity symbol, and there should be two iterations because there are three vertices, and the number of iterations performed at most equals number of vertices minus 1, as mentioned before. Step 2 is to begin the first iteration. As I mentioned earlier, we can update a weight only if the current weight is greater than the new weight. When going from A to B and C, we can see that the infinity is greater than 2, so we can update B as 2, and A to C is 5, so we can update C as 5, as infinity is also greater than 5. When considering node B, no changes will happen because as you can see there is no path starting from node B. There is another path for reaching node B from A to C and C to B. As the total weight, we can get 5 plus 1, which is equal to 6. And then we can check whether we can update the current path of B. Because 2 is greater than 6 is false, we cannot update the current path. So, B will remain at 2. The third step is to start the second iteration. When we are doing the second iteration as we did the first iteration, we can see that in the second iteration nothing will change. So we can say that we have found the shortest path from source node, which is A, to other vertices, which is B and C. Now let's take an example graph to see how Bellman-Ford algorithms works in real time. On this directed weighted graph, as you can see, there are 5 vertices such as A, B, C, D and E. Therefore, we can calculate the number of iterations like V, which means the vertex, minus 1. So, it will be equal to 5 minus 1 equals 4. So, the number of iterations that should be performed at most is 4. Now, let's see what will happen after each iteration. Initially, we can assign A as 0 because A is the source and source itself will be 0. And B, C, D and E nodes will be assigned to the infinity symbol because the paths are still not defined. In iteration 1, from A there are 2 paths, A to B and A to C, and 4 is less than the infinity, so this is false. Because of that we can update this and this will become 4. Same as that we can update C into A to C is 6 and this will be updated as 6. Now we can move on to B as there are no any paths from A to any other nodes. From B, there is a path to D as well as E. So D is going to be 4 plus 3 equals to 7 and E is going to be 4 plus 5 which is equals to 9. Moving on to C, we can update D as 6 plus 2, 8, but 7 greater than 8 is false, so we cannot update this. And C to B is 6 minus 5 which is equal to 1 and less than 4. Because of that we can update B into 1. Uh, from D, we can go to node E. So we can subtract 2 from D. So it will become 7 minus 2, which is 5. From E, there is no path going into any other node. So we can end the iteration 1. Now moving on to the second iteration, from A to B it is 4. No need to update because 4 is greater than 1. A to C is 6. No need to update. Then going into B, B plus 3 is D. So 1 plus 3 is 4. We can update this as 4. And 1 plus 5 is 6. So we cannot update E because the current shortest path is defined as 5. So we cannot update. That 6 plus 2 is 8. No need to update. 6 minus 5 equals 1. No need to update. Moving on to D, we can see that when we are subtracting 2 from D, which means 4 minus 2, we result in 2. So we can update because 5 is greater than 2. And same again, from E there are no paths, and we can end this iteration too. And when moving on to the third iteration, we can again calculate. From A to B 4, no need to update. A to C 6, no need to update. B to D 1 plus 3 is 4, no need to update. B to E 1 plus 5 is 6. Current shortest path is 2, so no need to update. C from C to D 6 plus 2 8, no need to update. 6 to B 6 minus 5 equals 1, so no need to update. D to E 4 minus 2 equals 2. And E to know any nodes, so iteration 3 will also end. After in iteration 3, no changes were made. This means that we now have the current shortest path to any node from A. But in here we can see that the number of iterations is 4. So we can stop at 3 or carry out with iteration 4, but the result will be same. Although the previously mentioned shortest path algorithms are great, there is a small problem. That is, the shortest path algorithms cannot handle negative cycles. If there is a negative cycle, the algorithm will be looped infinitely and therefore a shortest path cannot be defined. By using Bellman-Ford algorithm, we will be able to detect if there are negative cycles. I previously mentioned that the shortest path should be found on or before the v minus 1 iteration, which in v represents the number of vertices. So, if any additional iteration can be performed, it means that there is definitely a negative cycle in that certain graph. So like that, today's video comes to an end. Hope you found it helpful, and if you did, please like, subscribe and share this with your friends. If there are any feedback or questions about this video, please feel free to use the comment section. Thank you for watching and have a nice day.